is that how strong the evolution is, that one can see it with a naked eye. And in lithium 100 is much different. Of course, we were not the first. Mikhail Hayek was also studying TLD 300 in his thesis, looking at the top. He didn't do the convolutions, just looking at the top of the peaks. And this is an older result already in a high energy proton beam. So here comes the student for this work, Ivan Munoz. Where is Ivan? Well, I know that Ivan, there is Ivan. With this image convinced me that there was something very unexpected happening with TLD 300. These are 9 glow curves, 3 from our mammographic units and 3 from secondary standards laboratory. That's how Ivan worked. We decided to study the properties. These are irradiations in a mammographic unit, and he exposed in air, and he exposed in phantoms. Our parameter was just the ratio of high to low temperature peaks. So this area divided by this one. We also created a model and kept very rigorous a very rigorous deconvolution procedure. Here is the calibration. Things looked incredibly well behaved as the evolution of that relative ratio as a function of LET in this case, as a function of effective energy. This is one of the measurements that Ivan Munoz did in a mammographic phantom, going from the surface to 3.5 centimeters in depth. This is the LET value that we observe. LET decreases, and that corresponds to the hardening of the beam. Given a much solid foundation to this, he calculated LETs for the beams, the photon beams, and put them in the same graph as they have been obtained for ions. And we can see that except for the expected difference in changing particle, LET seemed to unify in a way both ions and photon results in terms of the high to low temperature ratio. We have done much more results: mammography, pediatric X-rays, radiotherapy, beams at 6 megavolts, machine, etc. And this is the work. I just want to mention 3 people, and I'm done. 3 people who have defined their own research lines after being students with us. One is Gerda, that as you hear later, she's trying now to understand the structure of the traps, doing very advanced solid state studies in lithium fluoride. Then Ivan at the German Cancer Center, he's also thinking on LET, now trying to find the signatures of LET in fluorescence nuclear track detectors using a confocal microscope. Fernanda Villegas, who is in Sweden at this moment at the Karolinska. She's one of the certified medical physicists at Karolinska. She's looking for her PhD thesis, alternatives to LET for an RBE model. That's it. I don't have more time. I can respond questions. I have to give thanks in the first time to this wonderful university. We received partial funding. The funding is always very small, extremely small. You will not believe how we carry our projects. And the most important part are the students. We have excellent students, and the national our National Science Foundation takes care of all the graduate students' scholarships. And that has been part of the reason of the success, having always more students that they were interested than the ones we can take. The Physics Institute has continuously supported us, my group and colleagues, Isabel Gamboa, Mercedes, Olga, Hilda, who had created their own research groups and just showing that what we learned, that we enjoyed it and we consider it very important. Thank you. And I apologize for the extra time. It was very difficult.
You illustrated very interesting low ARR for PLD 100 after exposure to heavy ions. But if you try to exposure PLD 600 into C and PLD 700 to take very difference.
The short answer is no. Okay, thank you.
Well, thank you. Thank you again.
Eduardo? Well, they only have this. Yeah, there's so many things happening. I don't know what this one. I have to remove this because okay, what is it?
Can I remove one of this? Esa es la primera. Puedo usar menos de esta aquí. Okay,
no, reject. I have lost it. The item, yeah. I have expulsar.
Yeah, they felt it. It could be ready. This one? Okay.
So the next talk is Professor Eduardo Yukihara from the PSI in Switzerland. So we'll speak about the theoretical consideration on the dose rate dependence on luminescence detectors. Go on.
Okay, thanks, Kelvin. So the motivation for this study that we did was, of course, the buzzword that is flash radiotherapy. So flash radiotherapy has been in the many articles and conferences in the last, let's say, 5 years, a little bit more, and it's based essentially on this effect that you get more sparing of healthy tissue if you deliver the dose at a higher dose rate than normally in certain conditions. So this, regardless of the reality of this effect or not, or in which condition it happens, this opens the question for us working with solid-state dosimetry of whether or not we can measure these high dose rates. So these developments require dose rate independent dosimeters. There's an increasing number of publications, there's ongoing animal and human trials, and all these new technical developments motivates this research. The conditions for us, what's important is the extremely high dose rates that can be achieved. So we're talking about doses still of the order of grays or tens of grays, but because the dose rate is so high, the pulses are so short, we can reach 10 to the third, 10 to the 6th grays per second instantaneous dose rate, or even more. The other field where this can be important also is in laser-based accelerators, where also the pulse can be extremely short, which means that the dose will be delivered in a very high dose rate. In the past, there has been studies that showed that experimentally that there were no dose rate effects in thermoluminescence and optical stimulated luminescence detectors. So these are some of these results that I could find, for example, on TLD100, lithium fluoride, on aluminum oxide, beryllium oxide, and in all of them, you don't see dose rate effects. We ourselves, we looked into this problem. We had a student, Silvia Mota, who did exactly a PhD on this topic. And her goal was to explore experimentally whether or not we could see those rate effects. And for that, she looked at the protons and electrons in 2 facilities. And here I'm not going to go present her all the results, but just a few snapshots of this. In proton beams, we did not see any dose rate effect. That was a work done by Jeppe Christensen, who is here also. And just showing the OSL deviation in terms of dose rate for different beams that we got. We did not see any dose rate effect. The 2 latest points showed the decreased response, but we think this was more because of the volume averaging of the detectors, because to achieve this dose rate, you have to make the beam narrower, and we have to apply corrections for that. Silvia Mota looked, one of her last studies, or I would say the most successful, was using a LINAC adapted to flash, converted to flash. And in that case, we irradiate several detectors simultaneously, so there's no dependence on the irradiation conditions. And we looked using a protocol that allows us to achieve high precision. We looked at several materials, and in all these materials, we did not see those rate effects. And here what you see is the dose per pulse, and there typically was 1 pulse that was delivered. And this work is documented in these papers. So TL, as you know, is the light emitted by radiation-induced trapped charge when stimulated. So essentially, we're stimulating these electrons that recombine, emit light. We can do dosimetry using these curves here, the calibration curve. And people try to write models for this. And some of the early models that looked into this, they did point out to the potential of those rate effects in TLD materials. This is one of the papers. The resolution doesn't allow you to read well, but it's from Guggenheim and Steve McKeever, where they looked into this simple one trap, one recombination center model, and you can write then rate equations for this process and try to calculate what happens in different conditions. And what they did see was a potential dose rate effect. So this graph here is plotted, the parameters here are related to the model, but essentially what you are seeing here is the number of electrons trapped at the end of the radiation versus the dose for different dose rates. And this is very interesting because you see for low dose rates, they see that you can have, as the dose increases, you can have less electrons trapped at the end. For high dose rates, you can have higher. So the behavior is completely different for high or low dose rates, which points to, is there a contradiction here? I mean, experimental results do not show any dose rate effect. Theoretical results point to the possibility of dose rate effects. So the last step of Silvia's thesis was to explore this issue. The question is, are these models that we looked at realistic? What could cause these dose rate effects? And what would a realistic model predict? Then these results that I'm presenting here were published already in this paper. The first step, of course, was to reproduce the results from the earlier papers. So this is just a figure to show that we obtained with this model the same results that were obtained in the past. And then we try to understand, first of all, are they realistic? And then you start seeing some interesting things that were not calculated in the original papers. For example, the TL curve. That's the TL curve that you get from using the same parameters of the original papers, but now calculating the TL curve. And one thing that you see here is this decrease right after the irradiation. Actually, in the paper, there's a radiation stage, there's a waiting time, and then you have the TL readout. And what you see here is for this relaxation time, if this is too short, like in the original paper, when you start reading, you still have charges recombining, and this causes this thermoluminescence here. And then you have the TL peak. If you increase the relaxation time, then you allow this charge to relax. That means you don't have any more charge in the conduction, the valence band, and then you have a low luminescence signal, and then you hit, you get this. But as you can see, even this curve is not typical from a TL material. I mean, you rarely see TL materials that have, with a single trapping center that has this shape of the curve. Does such model represent this real material? Then the answer is probably no, because we see here, this is the typical first order model, and you see the other curves that you get for different parameters or different doses with this model that I presented here before. So the TL peak is unrealistic and it changes the dose, something that we do not observe. And the dose response is extremely weird. I mean, this will be linearity, and that's the dose response you get for different dose rates with this model. I mean, if our materials would work like this, you could not use them for dosimetry. So the dose, they are dose rate dependent and it's non-linear. And then we try to look the concentration of charge, several parameters in the models. There's some bad connection here. Can someone help? I don't think it's here. I think it's... No, the computer is fine. The computer is showing. Is the connection with the projector. Yeah, it lost the connection with the projector. Remove it. Yeah. I can advance by telling the end of the story, maybe. So what we see in this model is that as you start irradiating material, you get a huge accumulation of electrons and holes in the delocalized band, in the conduction band, in the valence band. Something, again, that we do not see in real materials. And you can see that in this relaxation time. I mean, when after the relaxation that has this thermoluminescence emitting, which was due to recombination of this trapped charge, We don't see that. I mean, we see a kind of phosphorescence after you finish radiation, but that's typically related to shallow traps, not to charge in the conduction band and valence band. This charge, they relax very quickly. Let's see if I can get this to work again. Yeah. So that's what I was saying here. If you look at this curve here, there's a concentration of charges in the conduction band and valence band. And these are much larger than the concentration of trapped electrons or trapped holes. Once you finish the radiation, the relaxation time, you start with a huge concentration of conduction bands, electrons in the conduction band and holes in the valence band. So ultimately, she looked at different parameters and she concluded that that was the reason why those rate effects were being observed in these materials. I mean, it's a complex dynamics. It's difficult to explain exactly what's happening, but that's what's causing this dose rate effect. What happens if you use a realistic model? Well, we have such a model. We developed such a model many years ago to explain the dose response of aluminum oxide. And in that case, we had to consider the existence of what we call deep electron traps, deep hole traps, and the whole dynamic. So this, we had parameters that showed to reproduce the TL curves and those response curves of aluminum oxide. So we took the same model and looked, do we have those rate effects if we use this model? And the answer is no. For example, this is the TL response as a function of those. We see linear, superlinear saturation, and then this decrease. This effect is exactly what we were trying to explain at that time. I'm not going to go into this, but all these curves here are for different dose rates. So there's no dose rate effect, which shows that if you use realistic models in this case, we do not expect those rate effects. But at the same time that this shows that realistic models support the experimental results, it also hints at a possible dose rate effects in the future. Because as I said, what we say is that accumulation of charge in the conduction band and valence band is what led to those rate effects. Well, this relaxation here in trapping typically happens in time scales, let's say between 10 to minus 12, 10 to minus 10 seconds. So we speculate that if your dose rate is delivered at shorter times than this, you may end up in this situation where you do have accumulation of electrons and holes. In that case, we may have those rate effects, but for that, we'll have to achieve much higher dose rates that we see today. So we have to go to really femtosecond pulses to observe that. So in conclusion, the early theoretical models point out to dose rate effects when there's accumulation of charge in the delocalized bands. However, more realistic models do not predict those rate effects. And those rate effects could still be observable if the radiation time reaches the time scale of the relaxation process for these charges. So these are the conclusions. This our team in our department, and just make a commercial for the next presentations. There are several presentations from our department in the conference. I hope you can see them and attend them. Thank you very much.
Thank you, Eduardo. There's time for one question, but one question. Two, no. Okay, we will ask for
I have one.
Stephen.
Eduardo, the theoretical models that you describe as more realistic models depend on the relaxation times, depend on the concentration of defects, the capture cross sections. So how did you find realistic numbers for that? And does varying the concentrations of the cross sections affect the relaxation time?
Yeah, so Silvia looked at different parameters, but what we conclude is that whenever, so we play the parameters, change the parameters of the traps, etc. What she concluded, whenever we don't have this accumulation of charges, you don't have those rate effects. And the reason for this relaxation being so short is that once we start introducing more trapping centers, electron and holes or combination centers, then the electrons, they have immediately a path to recombine. So they will not accumulate. They only accumulate if you have this one trap, one recombination center and the probabilities are small and they don't have where to go. That's the reason why they accumulate in the localized bands. If you start adding like natural materials or realistic materials, more defects, they will go somewhere. That means we don't see this accumulation.
Okay.
Thanks.
All right. Thank you very much, Eduardo. Our next presentation is by Yuka Miyamoto from Chiyoda. Yuka will speak to us about the optical properties of silver-domed phosphate glass irradiated at high doses.
So this happened because we didn't have access to the computer to download the presentation for this session because the university was closed. Because it can be hard. So what is I can download this. What is the name of your presentation? You send it to, what is the name? What is the name of the email that you send? The email that you send, what is the email you send to your group? What is the title? Is it? Presentations. This is your? No, this is not your. Let's launch this.
Presentaciones que le mandó a la doctora ahorita, aquí están todas. Las de allá en Monterrey.
Let's download this. Yeah, when you are opening the picture, you actually copy everything. Okay, I will copy them. ¿Cómo se copia aquí?
Control C. Control C.
Okay.
Control V.
Cuando lo ponemos aquí, le ponemos una carpeta, ¿no? No se pone una carpeta.
Se puede crear una nueva etiqueta.
A ver. So now yours is this one. Okay. Yes. Okay. So now the next presentation is from, I should remove the name. Yuka Miyamoto from Japan, from Shoda Technical Corporation.
Thank you. Good morning, everyone. So this type is optical protected in edge-doped phosphate glass, irradiated with high doses of gamma rays. So this is the edge-doped phosphate glass. It's RPL glass exhibit luminescence radiation. So you can see this luminescence. So its characteristics is high sensitivity, low fading, and reusable. So we use this RP glass for the glass dosimeter. About 10 years ago, we reported this result. So it's a comparison of RPL spectra with high LED alpha particles. So it is so this point out this material exhibit a phenomenon known as LED quenching. So in this study, investigated whether RPL can be useful for LED environment by examining the spectral optical properties of RPL glass added with high dose of gamma rays and their mechanisms. Contains more experimental details, result and discussion, and conclusions. So use RP glass. So its glass is same the glass dosimeter. This photo taken under visible light. So gamma rays from cobalt 60. So 50 gray to 100 Q gray. So under the UV light, you can see the RPL fluorescence. First, three-dimensional matrix of the excitation and emission spectra. This method uses the analysis of absorbance, transmittance, excitation, emission matrix techniques. So, and second, excitation and emission spectra and radiative lifetime vision. So using this result, we observed each lifetime divided so in the RPL intensity. So first, three-dimensional control point of gamma ray radiates samples for doses ranging from the 50 gray to the 50 Q grade. So it's emission wavelengths and excitation wavelengths. Its yellow dash line is 55 nanometer. So usually we take a RPM, this RPM. So this excitation and this RPM, orange RPM and blue RPAs. Those includes and their RPA is included. And orange RPA is degrees from 1 kilogram. This intensity. So the collected RPL excitation and emission spectra from RPL plus after gamma ray irradiations. So excitation spectra and emission spectra, and blue RPL and orange RPL. This RPL glass has a multiple luminescence center. So it's an orange RPL and blue RPL and another. So those linearity of orange RPL and include linear and degrees about kilogram order. So those linearity of blue RPL include linear and become sublinear about kilogram order. So we measured the lifetime. So time to amplitude converter took 100 nanosecond this time. And this time is 340 microseconds and 11 milliseconds this time. So usually blue RPL lifetime is nanosecond order. The orange RPL was microsecond order and millisecond order. So this type increase and lifetime is degrees. So microsecond order and millisecond order is dot increase and lifetime is also increased. So we analyze the lifetime of each tag divided lifetime divide to so components. So divided to three parts. So it's 3 parts use the this analyze. So it's a trace the stochastic result. So this case is those 50 gray, and gray line and black line is emission spectrum. So blue lines were 100 nanosecond components, and green lines are 340 microsecond components. So this case, 50 kilogram order. So blue components and green components added red components. It's 11 milliseconds. So blue RPL divided main to peak there, and orange RPL divided main peak. So for is there. And so this chart is so so this line to 6 peaks wavelengths, and this color is inch, and each colors. So 1 kilogram, 10 kilogram, and 50 kilogram. That is 100 nanosec, 340 microsec, and 11 microsec. So blue RPL is increased, and orange RPL 600 nanometer is also increased. So interesting result is this. So it shows the lifetime and the quantity efficiency. Sorry. So 530 nanometers. It is green. Green RPL is so appear and degrees, and red RPL is appear. So conclusions: we investigate the optical properties and behavior of RPL sensor in this class, subject to high dose of gamma ray irradiance. This orange RPL includes linear with the include in dose and 10 degrees. The blue RPL also includes linear with the increase in dose and increased form. High dose irradiates at 50,000 nanometers for green RPL appear. So we discovered the first time that blue, green, orange, the RPL exhibit complex behavior such as a reduction, enhancement, and disappearance, and imagination wide and present these spectral profiles. We believe that the parameter of this study will be helps for evaluating LED values, which remains to the biological due to exposure to radiation. So thank you very much for your attention.
Only one question for Yuka. Okay, if there is no question, we move on. And the next talk would be about phototransfer thermoluminescence, bio first principle analytical method by Makaiko Chitambo from South Africa. This is we're going to you go back. It's two at once because
So in this talk, I want to offer some thoughts on how to measure and interpret the phototransferred thermoluminescence from beryllium oxide. We know that beryllium oxide is an important dosimetry material. First of all, let's start with the principles. Phototransferred thermoluminescence, as we know, is thermoluminescence that is produced owing to transfer of charge or transfer of electrons from a stable deep electron trap to a shallow trap that has been purposefully emptied. Now, this definition is only a tutorial definition. We understand the process, but this type of process is in fact just an exception. It's an experimental exception rather than the rule. And the reality when you measure phototransfer thermoluminescence from real materials is very, very different. I think let me make the presentation from here because I can't read from. So the reality is that the number of donors is often unknown, and concepts of a single isolated acceptor and a single isolated donor are actually they don't always work, and you can't always justify. So we need to dispense with that academic notion. So how do we dispense with that academic notion and then analyze the PTTL in terms of systems of acceptor and donors? Here are some 3 graphs that show measurement procedures. The first one that is labeled method 1 is a typical method where the illumination and the irradiation are done at the same temperature, and what separates them is just the preheating. So the preheating then clears the peak of interest. If the irradiation temperature is at a higher temperature than your peak, then the preheating becomes redundant. Same thing in method 3, where the illumination temperature is at a much higher temperature than your irradiation temperature. The common one, of course, you see is actually method 1. So with that, you can probably come up with a definition of phototransfer thermoluminescence that tries to take into account the experimental realities. And we can look at phototransfer thermoluminescence as a phonon-mediated temperature and wavelength resolved emission that arises at one electron trap because of the combination of a phonon-aided and a photon-mediated release of electrons. Why is that? The reason is that when you measure when you do illumination at room temperature, the phonon contribution is actually very little. So we tend to ignore that. However, when you then measure the TL, the TL exclusively involves phonons. Okay, so that's why you can actually get away with that definition. So some measurements. This here is a glow curve of beryllium oxide that we studied. It shows 4 peaks, four glow peaks, and when you do preliminary measurements of phototransfer thermoluminescence from this material, what you find is that the first two peaks, the first three peaks, in fact, peak 2 and peak 3 are produced by phototransfer. You don't see any phototransfer from peak 1, and whichever one of those that you see, you know, whether you use blue light or green light or UV light, whichever one you see depends on the combination of the wavelength of stimulation and the preheating temperature. So the graph on the right is just an example, an example of a measurement showing for phototransfer at peak 2. This table is just an index. It's just an index of those results then. And it's just showing a summary, a summary of which peaks come out for which combination of preheating and wavelength. So you can see that not all peaks are produced, and whichever peak you see in phototransfer depends on that combination of wavelength of stimulation and the preheating temperature. So in analysis, we then try to analyze the PDTL as a system of acceptor and donors without making any assumption about the source. Okay. The reason for this is that usually when you look at phototransfer from beryllium oxide in the literature, okay, the assumption has always been that phototransfer is generated from the deep electron traps. Okay, so in this case, we don't make that assumption at all. So if you're going to analyze the phototransfer, it then means that one has to have an idea of how many donors are contributing to that phototransfer and the identity of those donors. So what we do as a first step is to use pulse annealing, whereby you irradiate and you preheat a sample sequentially. And when you do that, using blue light, that is the sort of results that you get. So you can see that the change for peak 2 and peak 3 match. You know, as you lose signal from peak 3, so do you lose the phototransfer thermoluminescence from peak 2. So you can conclude that qualitatively, the electron trap for peak 3 is contributing to your phototransfer at peak 2. The change for peak 4 is very, very different, and it doesn't follow any of that. Very, very interesting. So if you're trying to match, then you can say, okay, peak 3 is a donor, but what about peak 3? Because peak 4 does not follow. So you can guess that there must be some other electron trap, maybe the deep trap, or maybe the change that you see the contribution of hot traps. This is with the blue light. When you do this with green light, 5259 nanometer, this is the sort of result that you get. The x-axis here is on a log scale. So that dynamic range is tending to depress the change in peak 4. But if you draw it on a linear scale, you can just see that, in fact, the change at peak 4 still tends to increase. Okay. So that's evidence of a competitor trap, because you don't see phototransfer at peak 4, and yet there's that kind of change. And so for analysis, I'm going to talk about one thing: how to analyze how to analyze PTTL time response profiles. And PTTL time response profiles, I just mean the intensity as a function of the stimulation time. So three methods. One can use a phenomenological model. You can use a kinetics model, but I'm also going to talk about how one can use vector fields. So first of all, let me show the profile for peak 2. And the behaviors there are typical behaviors where the phototransfer intensity increases and then decreases. Now, when you change the illumination wavelength, you see that in fact the change for peak 2 now departs from the typical behavior. Okay, so this then begs the question of, you know, how does one analyze this? And then more interestingly, here's the behavior for peak 3, where the intensities seem to increase continually. So with a phenomenological model, what you do is you look at the transport of electrons between a donor and an acceptor, and you simply write it in terms of the portion that is that ends up at the acceptor. So you can write you can write a family of rate equations, which in this case I've just written as a matrix, and with that matrix, you can work out the analytical solution. The advantage here is that you can look at the contribution from each donor and then decide if that contribution is important or not. Okay, so if that contribution is weak, you can work it out, or you can factor it in your matrix and simply solve the equation. So the analytical solution then is what is applied to data. Alternatively, if you have no knowledge of the importance of your donors, but you know the intensity, you can work out a ratio plot. I think in statistics, or they call this a blob program. So you can work out a ratio of your most intense donor to everything else. So as an example, let's look at the solid circles. So if we look at the solid circles, we see that although you can have a system of, say, 4 possible donors, mathematically, 2 of them, the contribution of 2 of them is just well below 20%, which means that they make very little contribution to your photo transfer. So you can estimate your system as being of 1 acceptor and 2 donors instead. Okay. This one is a fit, 1 acceptor, 2 donors. I see that the chair leader standing up, so I'll try and speed up. So this one then suggests that there's possibly an additional donor. Okay. With theoretical modeling, we know theoretical modeling, but in this case, we drop simplifying assumption and we include retrapping. The problem is that sometimes when you do that, it might not be realistic because you actually ignore the experimental behavior of your donors. Then with vector fields, you don't need to work out your solution. Okay. What you work out is the possible direction of your solution. So these are vector fields. The vector fields show us in which direction our solution is likely to go. Then let me very quickly move on to this one here about stability. So with stability, you are now looking at the relative concentrations of holes and electrons. Okay, and you can write a pair of differential equations that actually tell you what happens when there's an encounter between them. You then linearize them and find the critical points, and you then interpret what that critical point says. So in this case, holes and electrons cannot mutually annihilate, and there will always be an equilibrium value for both that is close to 0 but not actually 0. Okay, so if that is the case, then you can additively add to the number of holes, which means that you can get the sort of results that we saw for peak 3. Final slide. So in conclusion, the PDTL of beryllium oxide involves multiple donors and not just the deep electron trap. The time response profiles, we can look at them using phenomenological models as informed by experiment. But if you don't want to use any simplifications, of course, kinetics models and vector fields also describe experimental behavior. The role of some donors can be weak, but the contribution of all traps, including the quiescent ones, the optically quiescent ones, actually also contribute. And finally, the photo transfer involves whole traps. Thank you very much.
We thanks Makaiko, and the next speaker, there is no time for question. So if you have some question, you can take the opportunity during the coffee time. Thank you. So the next speaker is Rodolfo Ruiz from Universidad de Sonora in Mexico. How to move this? This is not working. The computer is freezing. Oh, no. I can see the presentation. Where's the guy, the technician? I cannot see where to move there is some problem with the control. I cannot see the mouse. ¿Puedes ver cómo se cambia la pantalla para sacarlo? No aparece aquí, pero aparece aquí. No, sí, esta presentación no nos podemos sacar. No se puede sacar eso para poder. Sin sacar eso para poder abrir la letra, como que se puso como imagen.
Good morning. Hello, everyone. And this is first impressions about the study of TL luminescence in hydroxyapatite. And we doped the hydroxyapatite with three elements: europium, dysprosium, and chromium. Here we have the TL response of hydroxyapatite that shows more or less 3 peaks around these places. But for dual right measurements that we try to do pretty sure that this luminescence is caused the beta radiation, we need to do ablation. We do this procedure 4 times, and we find that at the first time we get this peak. And when we doped the sample with chromium, the peak disappear. Okay, but appear a new peak around here called the chromium. Now, when we compare the HEP with another sample doped with europium, the europium moves the peaks to lower temperatures, but at the same time, we get the same peak with a fierce ablation. And with the dysprosium, the peaks by the ablation disappear again. Now we try to do combinations between these elements, mix europium, chromium, and dysprosium, dope it in the hydroxyapatite matrix, and we have this mix produce the same thing, moves the peaks to lower temperatures and a little low signal about the 360 degrees, maybe, well, in this case with the chromium europium mix, and with the chromium dysprosiums, the signal about the 300 is increasing. And when we combine the 3 elements, there is coexist this signal with another signals at low temperatures, but with dysprosium and europium appear again a little one signal when we do the ablation. Well, and what happened in the material when we dope it with 3 elements? Results that, yeah, we have hydroxyapatite, but at the same time, we have another phases. The phases what we found was calcite, batterite, and aragonite. And we have the same results in all the XRD. So these elements cause the proportion and the mixture and the HAP moves the XRD signals. In occasions, more calcite peaks, like here. In other occasions, is lower. Obviously, is caused these dopants. Dysprosium produce this, europium produce that, and chromium produce this. And the relations with the other phases, but aragonite, cause the same thing. This is another example of the rest of the samples. The XOD are modified by this doping. Well, it's a really fast chart. Where I try to take this presentation. This presentation is about this peak that is appearing in the relation. You can see it in the HEP undoped and here in this combination, this person europium, just with europium. So the europium permit that this peak appear exactly that doped sample. Now the only one not happen the same, and in the reference we found this Urbina. Sorry, Urbina says that he found a similar response like this Asian response of TL when he radiated a calcite with gamma radiation. And if we think about the background radiation, we have always gamma. So the hydroxyapatite is sensible to gamma radiation, and what we see in the samples is the background radiation. So this kind of material can be used for gamma radiation. At the same time, if you try to increase the signal, you need to use the sample doped with rubium. And that's it. I'm ready for your question.
Well, thank you, Professor Ruiz. Are there any questions for the speaker? All right, I see none, so thank you again. And now we break for the poster session, which is going to be held in the Amuskali lobby.
Amuskali building.
And we should be back here at noon, 12 o'clock, for the next invited speaker. So see you back here then. Thank you.
Please, for people, we'll have the talk for the next presentation. Come to download the presentation in the computer before going to the coffee break. Mari. In the Amuskali session, maybe you will find some guy. Ivan, can you guide him, please? There's you will find some other guy with a yellow shirt that can help you to the direction of the building. And also you can put your poster in, everything is there. Okay. No, bueno, y ese es el problema. El problema vamos a otra carpeta.
Sí, para hacer la parte que doctora, su presentación. Ah, ok. Ok, vale. Sí.
Entonces, por eso, una vez que termine la postura, la tomamos para que no se quede más de voy a poner a recargar un poco de esto para